In the vast emptiness between galaxies, a supermassive black hole is devouring cosmic gas streams, its gravitational pull bending light from billions of light-years away until the James Webb Space Telescope caught it in the act, revealing a cosmic feast unseen until now. Imagine a black hole so massive, its event horizon spans millions of miles, yet it's sipping on tendrils of gas colder than the void itself, each stream a river of hydrogen and helium flowing like liquid starlight. The Webb's infrared eyes pierce through the cosmic fog, spotting these ghostly filaments spiraling into the abyss, their glow flickering like dying embers. This isn't just a black hole feasting, it's a cosmic engine, converting invisible gas into the raw fuel for new stars, all while the universe watches, unaware of the silent storm raging in the dark. In the vast expanse of the universe, where galaxies swirl and stars ignite, there exists a cosmic phenomenon that has long captivated astronomers: the supermassive black hole. These colossal entities, millions to billions times more massive than our Sun, reside at the centers of galaxies, their gravity so intense that not even light can escape their grasp. For decades, scientists have studied how these behemoths grow, but a recent discovery by the James Webb Space Telescope has shed new light on their feeding habits. The telescope has captured evidence of a supermassive black hole consuming cosmic gas streams, a process that challenges previous assumptions about how these giants sustain their immense size. This finding is not just a milestone in astrophysics, it's a glimpse into the life cycle of galaxies themselves. Let me take you through this groundbreaking discovery and the implications it holds for our understanding of the universe. To grasp the significance of this observation, we first need to understand the role of supermassive black holes in the cosmos. These objects are not mere cosmic vacuum cleaners, they are central to the evolution of galaxies. Their growth is intricately linked to the availability of gas, the primary fuel for their expansion. Traditionally, scientists believe that supermassive black holes primarily fed by accreting vast clouds of gas, a process that releases enormous amounts of energy and influences the surrounding galaxy. However, this new discovery suggests a different mechanism at play. Instead of consuming large gas clouds, the black hole in question is feeding from narrow, high-speed streams of gas, a phenomenon that has been theorized but never directly observed until now. The James Webb Space Telescope, with its unparalleled sensitivity and resolution, has allowed astronomers to peer into the distant universe with unprecedented clarity. This particular observation was made of a galaxy located billions of light-years away, where the black hole's activity is visible in the infrared spectrum. The telescope's ability to detect faint light from ancient cosmic events has been crucial in revealing this process. The data collected by Webb shows that the black hole is drawing in gas streams that are not only incredibly thin but also moving at high velocities. These streams are thought to originate from the surrounding interstellar medium, where gas is heated and accelerated by the black hole's gravitational pull and the intense radiation from its accretion disk. What makes this discovery particularly remarkable is the scale and dynamics of the gas streams. Unlike the massive gas clouds previously thought to feed black holes, these streams are much narrower and more diffuse. This suggests a different mechanism for gas accretion, one that may be more efficient in certain environments. The observation challenges the existing models of black hole growth, prompting scientists to reconsider how these objects evolve over cosmic time. If supermassive black holes can sustain themselves by feeding on these narrow streams, it opens up new possibilities for understanding their role in galaxy formation and the regulation of star formation in their host galaxies. To visualize this process, imagine a cosmic dance between the black hole and its surroundings. The black hole's immense gravity creates a region known as the accretion disk, where gas spirals inward, heating up and emitting radiation. However, in this case, the gas isn't forming a traditional accretion disk. Instead, it's flowing in as narrow streams, possibly due to the presence of magnetic fields or the influence of surrounding structures like spiral arms or tidal tails. These streams may be guided by the black hole's magnetic field, which channels the gas into specific paths, allowing it to spiral inward more efficiently. This process is not only a testament to the power of gravity but also highlights the complex interplay between magnetic fields and gas dynamics in the universe. The implications of this discovery extend beyond the study of black holes themselves. Supermassive black holes are known to influence their host galaxies through a process called feedback, where the energy released during accretion can heat or expel gas, regulating star formation. If these gas streams are a common feature in the feeding process, it could mean that the feedback mechanisms are more nuanced than previously thought. The energy released from these streams might have different effects on the surrounding environment, potentially shaping the structure and evolution of galaxies in ways we haven't yet considered. This finding could lead to a re-evaluation of how galaxies form and evolve, particularly in the early universe when supermassive black holes were thought to have formed rapidly. Another fascinating aspect of this discovery is the role of the James Webb Space Telescope in capturing such detailed observations. The telescope's advanced instruments, including its near-infrared and mid-infrared cameras, have allowed scientists to detect the faint signals from these distant gas streams. The ability to observe in the infrared spectrum is crucial because the light from these ancient events has been stretched over billions of years, making it visible only in the infrared. This capability has enabled astronomers to study the early universe, where the first galaxies and black holes were forming. The data from Webb's observations not only confirm the existence of these gas streams but also provide insights into their composition and dynamics, offering a clearer picture of the conditions in the early cosmos. The study of supermassive black holes has always been a blend of observation and theory. While we have long known that these objects exist and influence their surroundings, the exact mechanisms of their growth have remained elusive. This discovery adds a new layer to our understanding, showing that the feeding process is more diverse than previously imagined. It also raises questions about the environments in which these gas streams form and how they interact with the black hole's magnetic fields. For instance, do these streams form in specific regions of the galaxy, or are they a universal feature of supermassive black holes? The answers to these questions could reshape our models of black hole evolution and their role in the universe's large-scale structure. Moreover, this observation highlights the importance of continued exploration with advanced telescopes like Webb. The ability to detect such subtle phenomena underscores the need for even more sensitive instruments in the future. As we refine our observational techniques, we may uncover additional mechanisms by which black holes grow, further enriching our understanding of these cosmic giants. The study of supermassive black holes is not just about understanding their individual properties, it's about unraveling the intricate web of forces that govern the universe. Every new discovery brings us closer to answering fundamental questions about the origins and evolution of galaxies, stars, and the very fabric of spacetime. In conclusion, the James Webb Space Telescope's observation of a supermassive black hole feeding from cosmic gas streams represents a significant leap in our understanding of these enigmatic objects. By revealing a new mechanism for black hole growth, this discovery challenges existing models and opens up exciting avenues for research. It reminds us that the universe is full of surprises, and that our quest to understand it is far from over. As we continue to explore the cosmos with tools like Webb, we are not just uncovering the secrets of black holes, we are peering into the very origins of the universe itself. This discovery is a testament to the power of human curiosity and the enduring pursuit of knowledge that drives scientific exploration. The James Webb Space Telescope, launched in December 2021, has revolutionized our ability to peer into the cosmos. Its advanced instruments, designed to capture infrared light, have allowed scientists to observe distant celestial objects with unprecedented clarity. One of its most groundbreaking discoveries involves a supermassive black hole at the heart of a distant galaxy, feeding on cosmic gas streams. This finding, made possible by the telescope's unique capabilities, has provided critical insights into how these massive entities grow and influence their surroundings. But how exactly did scientists uncover this process? The journey began with the James Webb's ability to detect faint, distant light, a feat made possible by its large mirror and sensitive instruments. By capturing infrared radiation, the telescope can peer through cosmic dust and observe regions of the universe that were previously shrouded in darkness. This capability was essential in identifying the subtle signatures of gas streams feeding a supermassive black hole. The discovery was not the result of a single observation but a complex interplay of technology, data analysis, and scientific collaboration. Scientists first used the telescope's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, to gather high-resolution images and spectra. These instruments allowed them to detect the faint glow of gas as it spiraled toward the black hole, a process that emits specific wavelengths of light. However, the data collected by the telescope alone was not enough. To confirm the findings, researchers combined Webb's observations with data from other telescopes, including the Hubble Space Telescope and ground-based observatories. This multi-wavelength approach helped paint a more complete picture of the black hole's environment. The process of analyzing the data was equally intricate. Scientists had to sift through vast amounts of information, using sophisticated algorithms to isolate the signals from the gas streams. They looked for patterns in the light emitted by the gas, which revealed its motion and composition. By studying these patterns, they could determine how the gas was interacting with the black hole and how it was being accelerated into the accretion disk. This required not only advanced technology but also a deep understanding of astrophysical processes. The timeline of this discovery is also noteworthy. The James Webb Telescope began its scientific operations in July 2022, and the observations that led to this finding were conducted over several months. The data collection process was meticulous, as the telescope had to capture light from an object billions of light-years away. The team of scientists involved in this research had to wait for the data to be processed and analyzed, a process that took months to ensure accuracy. The significance of this discovery lies in its implications for our understanding of black hole growth. Supermassive black holes are thought to play a crucial role in shaping galaxies, and their growth is often linked to the availability of gas in their surroundings. However, the exact mechanisms by which they accrete matter have remained elusive. This observation provides direct evidence that gas streams can feed these black holes, offering a new perspective on their evolution. The discovery also highlights the importance of long-term observations. While the James Webb Telescope has been in operation for just a few years, its ability to capture data over extended periods has allowed scientists to study processes that unfold over millions of years. This is particularly important for understanding phenomena like black hole accretion, which occur on cosmic timescales. The role of collaboration in this discovery cannot be overstated. The James Webb Telescope is a product of international cooperation, and the research that led to this finding was no different. Scientists from various institutions and countries worked together, sharing data and expertise to interpret the observations. This collaborative effort was essential in overcoming the challenges of analyzing such complex data. The process of confirming the discovery also involved cross-checking results with theoretical models. By comparing the observed data with simulations of black hole accretion, scientists could validate their findings and refine their understanding of the process. This interplay between observation and theory is a hallmark of scientific discovery, ensuring that each finding is grounded in rigorous analysis. The implications of this discovery extend beyond the study of black holes. Understanding how these massive objects grow can provide insights into the formation and evolution of galaxies. Supermassive black holes are often found at the centers of galaxies, and their activity can influence star formation and galactic structure. By observing how they feed on gas streams, scientists can better understand the feedback mechanisms that regulate galaxy growth. This, in turn, helps us piece together the history of the universe and the processes that have shaped it over billions of years. The James Webb Telescope's ability to capture such detailed observations has opened new avenues for research. Future studies will likely focus on identifying more instances of black holes feeding on gas streams, as well as exploring the conditions under which such processes occur. This could involve studying the role of dark matter in guiding gas toward black holes or investigating the impact of environmental factors on accretion. The discovery also raises questions about the diversity of black hole feeding mechanisms. While this observation provides evidence of one method, there may be other ways in which black holes acquire mass. Future research will aim to uncover these variations, shedding light on the full range of processes that govern black hole growth. The significance of this finding also lies in its demonstration of the power of modern astronomical technology. The James Webb Telescope represents a major leap forward in our ability to observe the universe, and its capabilities have enabled discoveries that were once thought impossible. As scientists continue to analyze the data collected by the telescope, they are likely to uncover even more surprises, further expanding our knowledge of the cosmos. In conclusion, the discovery of a supermassive black hole feeding on cosmic gas streams is a testament to the ingenuity of modern astronomy. It highlights the importance of advanced technology, collaborative science, and meticulous analysis in uncovering the mysteries of the universe. The James Webb Telescope has provided a new window into the cosmos, allowing us to witness processes that unfold on a scale beyond our imagination. As we continue to explore the universe with tools like this, we are not only expanding our understanding of black holes but also deepening our appreciation for the vast and complex systems that govern the cosmos. Webb catches supermassive black hole feeding from cosmic gas streams. This part of our deep dive into Webb catches supermassive black hole feeding from cosmic gas streams focuses on go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Webb catches supermassive black hole feeding from cosmic gas streams. This part of our deep dive into Webb catches supermassive black hole feeding from cosmic gas streams focuses on give historical context, how our understanding of this general topic evolved over past decades, earlier missions, or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The James Webb Space Telescope has given us a rare glimpse into the life of a supermassive black hole, revealing how it feeds on cosmic gas streams. But while this observation has provided groundbreaking insights, it has also raised more questions than answers. Scientists are now grappling with the mysteries of how these gas streams form, how they sustain such massive black holes, and what this means for our understanding of galaxy evolution. The data from Webb's instruments has opened a new chapter in astrophysics, but it's far from the final story. For instance, the exact mechanism by which the black hole captures and consumes these gas streams remains unclear. Are these streams a common phenomenon, or are they an exceptional case? How do they interact with the surrounding galaxy, and what role do they play in the black hole's growth? These questions are not just academic, they have profound implications for our understanding of how supermassive black holes, which are thought to reside at the centers of most galaxies, have grown to their immense sizes in the early universe. The observation also challenges existing models of accretion, the process by which black holes pull in surrounding material. Traditionally, accretion disks have been considered the primary mechanism for feeding black holes, but the Webb data suggests that gas streams might be a critical, perhaps even dominant, factor in some cases. This raises the question, are these streams a new piece of the puzzle, or are they simply a more extreme version of a process we've already observed?
The answer could reshape our understanding of black hole growth and its role in shaping the cosmos. Another unresolved issue is the origin of these gas streams themselves. Where do they come from, and what conditions allow them to persist long enough to feed a supermassive black hole? Some theories suggest that these streams may be remnants of ancient galaxies that have been torn apart by the black hole's gravitational pull, a process known as tidal disruption. Others propose that they are the result of mergers between smaller galaxies, which could funnel gas toward the black hole. However, the Webb observations have not yet provided definitive evidence to support any single hypothesis. The data shows the presence of gas streams, but the exact mechanisms that generate and maintain them remain speculative. This ambiguity highlights a broader challenge in astrophysics. While we can observe the effects of these processes, the underlying causes are often obscured by the vast distances and timescales involved. Additionally, the role of dark matter in these interactions is still a topic of debate. Dark matter, which makes up the majority of the universe's mass, is thought to influence the distribution of gas and the dynamics of galaxies. However, its direct role in feeding a black hole via gas streams is not yet understood. Some researchers speculate that dark matter could act as a gravitational scaffold, guiding gas into the black hole's vicinity, while others argue that its influence is too indirect to play a significant role. Without direct observations of dark matter's behavior in these environments, these questions remain open. The implications of these unresolved mysteries extend beyond the black hole itself. The way a supermassive black hole feeds can have far-reaching effects on its host galaxy. For example, the energy released during accretion can drive powerful jets of particles and radiation, which in turn can heat or expel gas from the galaxy, affecting star formation. However, the Webb data suggests that the feeding process might be more complex than previously thought. If gas streams are a major source of fuel, their impact on the galaxy's evolution could be different from what current models predict. This raises the question, are we missing a key component in our understanding of how galaxies and their central black holes co-evolve? The answer could have profound consequences for theories about the formation of large-scale structures in the universe. Another area of debate centers on the timescales involved. The Webb observations capture a snapshot of a black hole feeding, but the process of accretion is likely an ongoing, dynamic event. How long does it take for a black hole to consume a gas stream, and what happens after? Do these streams replenish themselves, or are they one-time events? The data from Webb provides a glimpse into the present state, but it doesn't reveal the full timeline of the black hole's feeding history. This limitation underscores the challenges of studying such distant and dynamic processes. Scientists must rely on indirect evidence and theoretical models to piece together the story, which means that many aspects of the process remain uncertain. Furthermore, the observation of this particular black hole raises questions about its uniqueness. Is this a rare occurrence, or is it representative of a broader trend? If gas streams are a common mechanism for feeding supermassive black holes, then our understanding of how these objects grow must be revised. However, if this is an exceptional case, it could indicate that there are multiple pathways for black hole growth, each with its own set of conditions and mechanisms. Determining the prevalence of such feeding processes requires more data from other regions of the universe, which is where future observations with Webb and other telescopes will play a crucial role. The scientific community is also divided on the potential for these observations to challenge existing theories. Some researchers argue that the discovery of gas streams feeding a black hole could lead to a paradigm shift in how we think about black hole accretion. Others believe that the data fits within the framework of current models, albeit with some adjustments. This debate reflects the broader nature of scientific inquiry, where new evidence can both confirm and refine existing theories, while also opening up new avenues of exploration. The unresolved questions surrounding this observation are not just about the mechanics of black hole feeding, they are about the fundamental processes that shape the universe. By studying these phenomena, scientists hope to uncover the intricate relationships between black holes, galaxies, and the cosmic web that connects them. However, the journey to answers is far from complete. Each new observation brings more questions, and the mysteries of the cosmos continue to inspire both curiosity and humility. As the James Webb Space Telescope continues to send back data, it is clear that the story of supermassive black holes and their feeding mechanisms is still unfolding. The answers we seek may lie not just in the data we have, but in the next discoveries waiting to be made.
Webb catches supermassive black hole feeding from cosmic gas streams. This part of our deep dive into Webb catches supermassive black hole feeding from cosmic gas streams focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Webb catches supermassive black hole feeding from cosmic gas streams. This part of our deep dive into Webb catches supermassive black hole feeding from cosmic gas streams focuses on briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.